Welcome to Numerical Methods for Scientists and Engineers. Video 9. Direct Solution Methods. Tridiagonal System of Equations. Tridiagonal systems of linear equations are encountered in various fields such as numerical solution of ordinary and partial differential equations using finite difference methods. In structural engineering, in calculating stiffness and displacement in beams or grids. In fluid dynamics when solving CFD and transport equations. In electrical circuits, network analysis, and so on. A tridiagonal system of linear equations refers to a system of equations where the coefficient matrix is a tridiagonal matrix. This matrix has non-zero entries only on the main diagonal, one diagonal above and one diagonal below. Here, the array D denotes the diagonal array, B denotes subdiagonal array, and A denotes superdiagonal array. The other entries of the coefficient matrix are zeros. The array C denotes the right-hand side vector. The augmented matrix is set up as follows. The Thomas algorithm employs the Gauss elimination procedure specifically for tridiagonal systems of equations. The forward elimination procedure is employed to eliminate the subdiagonal elements. The first step is to eliminate B2, the element below D1, which is accomplished by multiplying the first row by minus B2 over D1 and adding it to the second row. This zeroes out the first column second row element. In the meantime, the diagonal element D2 and the right-hand side element C2 are updated as a result of the row operation. Here we used prime notation to denote the updated or modified elements. However, in practice, the modified elements are stored in the same array and the same memory address. Next, we wish to eliminate B3, the second column, third row element. This is realized by multiplying the second row by minus B3 over D2 and adding it to the third row. Here D2 prime denotes the memory address of D2. This row operation zeroes out the second column third row element, while updating D3 and C3. Basically, repeating the outlined row operations in the same manner transforms the tridiagonal system into an upper triangular form. The diagonal elements of the matrix and right-hand side vector are modified and their memory values are updated accordingly. The forward elimination process can be generalized as follows. Likewise, the back substitution involves only the diagonal and the right-hand side arrays, as well as the superdiagonal array A, which is not altered during forward elimination procedure. The back substitution can be employed as follows. This formulation can be made more memory efficient by eliminating the array X and overriding the solution on the right-hand side array C. This version requires only 4 arrays of maximum length n. The forward elimination and back substitution procedures can be expressed as follows. In pseudocode 2.13, arrays D and B are destroyed, that is, overwritten with the new values. When solving a tridiagonal system of the form AX sub m equals B sub m, where B sub m changes, the original arrays D and B must be stored with different names, say D0 and B0, and retrieved each time before calling the module tridiagonal. The advantages of the Thomas algorithm are: it is simple and easy to implement. It is a direct solution method. The computation is fast because arithmetic operations are minimum. It requires much less memory in comparison to full matrix storage. It is stable for well-conditioned systems. On the other hand, its handicaps are: the algorithm assumes that the diagonals are non-zero. The algorithm does not incorporate pivoting. It is applicable to only square coefficient matrices. For large or ill-conditioned systems, the round-off error can be a major problem. The LU decomposition of a tridiagonal matrix decomposes, or factors, the matrix into the product of two matrices, a lower triangular matrix L and an upper triangular matrix U, each with two diagonals. The elements of L and U are found using the following recursive relationships. This decomposition is particularly useful for solving systems of linear equations because once a matrix is decomposed, the multiple linear systems having the same tridiagonal coefficient matrix can be solved more efficiently by using forward and backward substitution. For a tridiagonal system of linear equations, the LU decomposition takes advantage of the structure of the matrix to minimize computational complexity, much like the Thomas algorithm does. The forward and backward substitution procedures are employed as follows. The Cholesky decomposition is a tridiagonal matrix decomposition that factors a positive definite tridiagonal matrix into the product of a lower triangular matrix, having non-zero diagonal and subdiagonal elements, and its transpose. The elements of matrix L are obtained by comparing and matching the matrix product of L and transpose L. This leads to the following algorithm, where the diagonal and subdiagonal elements are updated using the given simple recursive relationships. Then the forward and backward substitution procedures are employed as follows. Consider the following 6x6 tridiagonal system of equations. We first set up the augmented matrix, and we wish to zero out the -2 in the second row of the first column. We can achieve this by adding the first row to the second row. While creating a 0 in the second row first column, the diagonal and the right-hand side elements are updated accordingly. Next, to eliminate the 6 in the second column third row element, we add minus the second row to the third row. Accordingly, the diagonal and the right-hand side array elements of the third row are updated. Then, we want to eliminate the 14 in the third column fourth row element. To do that, we add -2 times the third row to the fourth row. As a result, the diagonal and the right-hand side elements of the fourth row are updated. To eliminate the -6 in the fourth column fifth row element, we add the fourth row to the fifth row. To eliminate the -11 in the last row of the fifth column, we add row 5 to row 6. Now the resulting system is an upper tridiagonal system, which can be expressed in equation form as follows. We note that the last equation has only one unknown, x6, and can simply be found as. Once we substitute x6 into the above equation, we can solve it for x5. Likewise, we substitute x5 into the above equation and solve it for x4. Substituting x4 into the above equation, we find x3. Substituting x3 into the above equation and solving for x2, we find. Finally, we substitute x2 into the first equation and solve it for x1, which finalizes the solution using the Thomas algorithm. That is all for now. See you next time with another topic. Bye.